Hello, everyone, and thank you for joining us today. My name is Renee Eveland, and I will be your host for this NASA Technology Transfer Program webinar on pressure, temperature, and recession measurements in extreme environments. Our presenter today is Dr. Robert Okogie. Dr. Robert Okogie received a bachelor's degree, a master's degree, and a PhD in electrical engineering from the New Jersey Institute of Technology in Newark between 1991 and 1996. He was a senior research scientist at Coolite Semiconductor Products in New Jersey from 1993 to 1997, developing high-temperature ohmic contacts to silicon carbide semiconductor pressure sensors for high-temperature applications. He was a senior research engineer at Ford Microelectronics in Colorado Springs in 1997, developing MEMS-based sensors, smart fuel injectors, and associated packaging technologies. In August 1999, Dr. Okogie joined the Silicon Carbide Research Group at NASA Glenn Research Center in Cleveland, Ohio, as an electronics engineer, primarily developing enabling technologies for silicon carbide microsystems for extreme environments. He served as the Associate Project Investigator in Hypersonic Project Experimental Capabilities of the NASA Fundamental Aeronautics Program between 2006 and 2009. Dr. Okogie was inducted into the NASA Inventors Hall of Fame in 2020, received the NASA Glenn Research Center Distinguished Publication Award in 2012, the Abe Silverstein Medal for Research in 2009, and numerous other awards between 2002 and 2018. Dr. Okogie is a senior member of the IEEE and has published over 50 peer-reviewed papers in scientific journals and conference proceedings relating to high-temperature MEMS technology, and was a contributing author to the CRC MEMS Handbook. Dr. Okogie has mentored over 20 student interns since joining the agency. Following Dr. Okogie's presentation, I will be giving a short presentation on how NASA licenses technology to outside organizations. Before we get started, I'd like to point out that your microphones will be muted throughout this presentation. So if you have any questions, please type them into the chat box in the lower right corner of your screen, and we will answer them during the Q&A session at the end. And now Dr. Okogie will present on NASA's pressure, temperature, and recession measurements in extreme environments.
Thank you very much. My name is Robert Okogie, and today I'll be talking about pressure, temperature, and recession measurements in extreme environments. I am a member of the Smart Sensing and Electronics Systems branch, which is part of the Communications and Intelligent Systems Division at NASA Glenn Research Center in Cleveland, Ohio. So today I'll be talking about a broad range of work we have done with regard to pressure sensors and briefly the advancement we have done in terms of developing new and emerging recession sensors for various applications, including hypersonics and entry and re-entry vehicles. Yeah, here's the outline of my talk. I'll talk about the application drivers, why silicon carbide for high temperature sensing, technical and technological challenges, silicon carbide pressure sensor characterization, field validation, recession sensor characterization, and conclusions. So in terms of application drivers, there's a broad range of application space where silicon carbide pressure sensors can be used, particularly in the harsh environments associated with a lot of these systems and environments that you find on this slide. In turbine engines, it will be used for thermoacoustic instability studies. Also, it could be part of the active combustion control and also exhaust noise emission. As you know, there's an active effort to reduce the emission of harmful gases such as hydrocarbons into the environment. So the use of pressure sensors is crucial in the monitoring and measurement of pressure conditions in the combustion chamber. That's part of the combustion chemistry. For Mars, we're looking to insert this pressure sensor as part of the atmospheric dynamics measurement. On Venus, temperature is about 460 degrees centigrade. The environment, the atmosphere is aggressive, has aggressive chemistry. Pressure is in the neighborhood of 90 bars, which is essentially 90 atmospheres, Earth atmosphere. We're also looking at using the pressure sensors for combustor instability studies, also as part of the mode transition studies, when one transitions from low speed combustion to high speed. We're also experimenting in the application of micro recession sensors for entry and re-entry. So basically, these sensors will be inserted in the forward section of the thermal protection systems of the space vehicle, so that it will adequately and effectively monitor in real time the recession rate of the thermal protection systems. This will allow system engineers to essentially monitor in real time the health of the thermal protection systems during re-entry. We're also looking at pressure measurements in a pulse detonation engine. Also application in geothermal environments, particularly when the system is monitored at somewhere in the neighborhood of 6 to 10 kilometers down Earth. Pressure at that point is about 20 KSI, and temperature approaching 300 degrees centigrade. We are also in the process now to explore the radiation resiliency of these pressure sensors as part of the advanced instrumentation for terrestrial and planetary-based nuclear reactors. So there's a broad range of application space for this technology. So why silicon carbide? A quick overview is what you see here. In this column here is silicon carbide. Next is silicon, diamond, and gallium nitride. I have basically highlighted key properties of silicon carbide that are critical for use as a pressure sensor. And you can see that to a large extent, its performance is far superior than the conventional silicon and gallium nitride, particularly in the energy band gap. In silicon carbide, it ranges from between 2.3 to 3.4. In our case, we are using the 4H polytype with a band gap of 3.2 eV. The Young's modulus is very high, between 300 and 500. And as far as the thermal conductivity is concerned, it's also competitive. The only material that has a higher thermal conductivity in this category is diamond. It's near inert as far as surface chemical reaction is concerned. It's also compatible with MEMS fabrication processes. In terms of availability and cost, I am rating this fair to good. Obviously, relative to silicon and relative to silicon technology or silicon crystal, it's still behind in terms of availability and cost. So you put all this together, you begin to look at trade-offs. If you want a device that operates beyond the capability of silicon technology, silicon carbide is the material of choice, and that's the main reason why we are basically adopting silicon carbide as the material of choice for extreme environment sensing. So my discussion here is going to be based on how to use this technology for temperatures beyond 500 degrees centigrade. This chart gives one a a broad understanding and appreciation of why, again, we are using silicon carbide. Basically, at lower temperatures, obviously, the material of choice is silicon due to its high gauge factor. However, as one moves to the right, to higher temperature regime, the application of silicon essentially falls off, and while silicon carbide continues to the extent that up to 800 degrees C, silicon carbide is essentially the only material that is still viable for use as a strain measurement material, with gauge factor ranging from 5 and above. So the challenge, beyond the choice of material, has to do with the stability of the metal contact, and also the packaging strategy that one has to adopt to support a stable pressure sensor at high temperature. So these two challenges are essentially what we worked on over several years to overcome the stability problems associated with the contact metallization and packaging. The success of this work resulted in the demonstration of the silicon carbide pressure sensor at 800 degrees centigrade. So what are the technology challenges as one approaches higher temperature beyond conventional environments that silicon operates in? First is the thermomechanically induced stress that exists in a package as one goes up in temperature. Like I stated before, the reaction kinetics of the contact metallization becomes quite aggressive. As a result of these two drivers, results in these failure mechanisms: cracking due to the CT mismatch, die-attached delamination, wire bond weakening due to intermetallic diffusion, low temperature eutectic formation, vibration-driven fatigue, unstable Ederico constant resistance. Combined, these failure mechanisms result in electrical and mechanical failure. So what have we done? We have developed an integrated silicon carbide and pressure sensor that has been demonstrated to operate at 800 degrees centigrade. This is the standard package that we're using currently. Somewhere at the tip here is the on-chip integrated temperature sensor and the temperature and the pressure sensor. So what does that offer you? First of all, this sensor does not require cooling because of the fact that we're using silicon carbide, and we have also developed the packaging and metallization that will support high temperature operation. It is integrated, which allows for accurate pressure and temperature relationship, real-time temperature compensation, and voltage to pressure conversion in real time. So it eliminates the need for post-test analysis and post-test voltage to temperature conversion. So this can be done right, in real time as measurement is conducted. Because of its ability to operate at high temperature, it allows for a closer insertion towards the combustion chamber, if that's the environment of, if that's the measurement environment. As a result of that, because of its closeness to the combustion chamber, it's able to capture the full bandwidth of the pressure transients of the flow field. This is due to the direct interaction between the sensor and the flow field. The advantage of this is that, unlike the conventional practice where an infinite tube probe is inserted into the combustion chamber and the pressure is piped all the way out to like 20 feet to where the conventional sensor resides, because a tube is essentially an acoustic filter the pressure, some frequency components, within the pressure transients could potentially be attenuated through, in the tube as the pressure transverses through the tube. This device essentially gets rid of that negative possibility because the sensor is in direct contact with the flow field. One unique characteristic of this device is that it has no wire bond. So it's a direct chip attached. You want to think about it as a flip chip concept. So here are some of the characterizations that were performed on both the temperature sensors and the pressure sensors. On this left chart here, there are 3 different temperature sensors from 3 different devices. So we basically looked at the linearity of the temperature sensors as a function of temperature up to 800 degrees C. And with that, we were able to extract the sensitivity of each of the sensors. To my right here is a representative plot of a pressure sensor that was tested up to 800 degrees centigrade. One thing that's of interest here that we are taking advantage of is the fact that at room temperature, which is this black plot here, you have the value, the net output at pretty much near 12 millivolts. But look at what happens at 800 degrees C. The output at 800 degrees C is pretty much in the neighborhood of 18 millivolts. So in essence, this device likes to operate at heart. So we want to take advantage of this unique phenomenon whereby this device operates at a higher pressure sensitivity at higher temperature. Further to the characterization of this device, we did some thermal cycling. The right chart here, we have thermally cycled this device at 600 degrees C. What you see here is essentially 3.5 cycles, or pretty much close to 4. Cycling up to 600 degrees C and cooling, and back to 600 and room temperature. And we did that over, like I said, over 4 cycles, basically to look at the null shift, the thermal null shift at key calibration points, which is room temperature and 600. And for all practical purposes, this device remained practically stable at the 2 critical calibration points. The rise time spikes that you see here are just due to the over temperature correction of the temperature controller. Something that we need to pay attention to is the gradual increase of the temperature sensor during cycling, and we understand that this was due to the fact that the temperature sensor needs some further burn-in order to maintain an appreciable stability. On the left-hand side here, we basically cycled the device at different temperature regimes, 600, 700, 800, 500, and 400. So for 800, the application space is essentially for short duration, particularly, for example, for access to space in the combustor engine of a rocket, or for high-speed vehicles, where the travel range or the application time is essentially either a few minutes to less than an hour. We have also looked at the dynamic response of this device, and what we did here was to compare the device performance against a water-cooled PCB piezoelectric pressure sensor, which is in red, and black is the response of the silicon carbide pressure sensor. And as you can see, up to 600 degrees C, the sensor is still responding to the dynamic events to the extent that we were able to extract the average pressure values, which in this case is at 1.88 psi, and the time excursion here is essentially at 100 Hertz, which is what you see here. Looking at the frequency domain, on the left-hand side here is the response of the frequency response of the pressure sensor. And as you can see, at 100 Hertz, it had very excellent response at different temperatures. Obviously, at 800 degrees C, at 600 degrees C, the response was lower than the response at room temperature. But we're still able to extract the frequency response. Unlike the PCB, we have to remember that the PCB is a very, very sensitive material, and as a sensor, I would say it's ultra sensitive. However, it is temperature sensitive, and the ultra sensitivity of the PCB can also become its disadvantage because it's water cooled, with water flushing around the PCB crystal. The crystal itself will hear, quote unquote, hear the turbulence of the water flow as a pressure transient. So it's actually measuring the pressure transient of the turbulence of the water flow, and that is what's captured here as what we describe as a vortex noise. In addition to, of course, the frequency response at 100 psi. Unlike in silicon carbide, you do not see such capture of the vortex. We have done some field validation, going from breadboard now to validating the device in the field. This is a standard combustor here at NASA Glenn that we're using. This is the combustor air section here, and this is the airflow path and the injector part here. And the sensor basically is residing somewhere here and also here. The PCB is residing here. So we are pretty much close to the combustor. And what you see here on the top chart here is the response of the PCB, which essentially captures the 310 thermoacoustic instability. Similarly, the silicon carbide pressure sensor was also able to capture the same 310 Hertz thermoacoustic instability. Further test in the combustor rig also confirms the performance of the silicon carbide pressure sensor relative to the PCB. On this top row here is the performance of the TCB at two different test regimes. Again, you can see that the key frequency of interest is what you see here, which is captured by the PCB at the two different tests. Also, similarly, the silicon carbide frequency response was also responded to the same frequencies as the PCB. The reason why the response of the silicon carbide pressure sensor was not as impressive as we have as we would expect at lower frequency is because, in fact, we did not use an optimized silicon carbide pressure sensor. This was essentially a silicon carbide pressure sensor that was not fully optimized to compete with the PCB. But we are happy with the fact that given the fact that it's not fully optimized, we were still able to grab the relevant frequencies. We have evolved to field characterization
into an actual jet engine. This is a DGen 380 engine. It's a 6-seater engine. What you're looking at here is the exhaust nozzle of the engine. Down here is the silicon carbide pressure sensor flush mounted to the nozzle. So in essence, it is in direct contact with the flow field. A magnification of this section here is what you see here in B. Just to, again, to give you an appreciation of where the sensor is relative to the flow field of the engine. On the other hand, outside of the engine, several conventional silicon pressure sensors were connected to infinite tube probes that extend from the nozzle to the outside, where these sensors, pressure sensors, were eventually located for obvious reasons, because these sensors, could not survive the hot sections of the nozzle, just as the silicon carbide does. So it has to be located. They had to be located at the benign section of the test environment, which is essentially at room temperature. So we compared the performance of this device against these 8 conventional pressure sensors. And that's what we see here. These 4 charts show the different power levels. The power here was at 50. This is 70. This is 80. And this is 90. And I just want to draw your attention to this bunch of plots here that represent the conventional pressure sensors. And these 2 plots here represent the silicon carbide pressure sensors. Again, across the frequency spectrum of interest, the silicon carbide pressure sensor was able to capture the same frequency components of interest as the conventional sensor across the different engine power levels. We have also looked at the viability of using this pressure sensor as part of the Venus atmospheric dynamics studies in the future. What I'm showing here is what is called the NASA GRC Extreme Environment Rig. In short form is GEAR, which is located here at NASA Glenn. This is a large chamber that essentially simulates Venus conditions as we know it today. Pressure, it can be pressurized to 1356 psia, temperature 460 degrees C. Like I stated before, nasty chemistry, nasty gases, CO2, nitrogen, sulfur dioxide, which is essentially acidic, and other nasty gases. So we're able to test this pressure sensor inside this chamber to simulate a Venus environment. And that's what we see here. After initially conditioning the chamber, the Venus condition was set at about 300 hours. And what you see here between 300 and about 850 hours, the duration during which the pressure sensor was monitored. You could see that within that time frame, the silicon carbide pressure sensor operated reliably from between 300 hours to about 550 or 530 hours. It continued operation beyond that, actually, to the end, to the termination of the test. However, operationally or functionally, the device will be said to survive operation from between 300 and 520. But operationally,
it actually survived the environment because there was no damage. There was no structural or physical or electrical damage to the sensor. This is the sensor head. That's the diaphragm up there. So there was no crack there. This is the package. However, the problem that resulted in its loss of proper functionality was because if you look at these wires here, you could see some crystal growth there. These crystal growths were actually nickel sulfide, which was the reaction between the sulfur dioxide and the nickel-coated, gold-coated nickel wire that was exposed to the environment. So this was the lesson we learned, that in the future, do not expose nickel wires to the Venus environment. If you do that, this is what you're going to get. You're going to get a bunch of nickel sulfide crystals. So as a result of this growth, it extended to the point where it was shorting out 2 wires out of the 4 wires that are coming out of the sensors. Nickel sulfide has good electrical conductivity, so which resulted in the shorting of the of the sensors. All right, I'm going to switch gear to talk about the progress we have made in developing minimally intrusive integrated recession sensors and temperature sensors, specifically for monitoring thermal protection systems for entry and re-entry vehicles. However, it has extended applications in where there's interest in measurements of ablation outside of TPS, attrition, brake wear, for example, sandpipe wear or sandpipe attrition. So any environment that has to do with the abrasion of the material will have a potential need for this kind of sensor. How does it work? This is the capacitive version of the technology. We have the resistive and the temperature version, but basically the way it works is that here's your capacitor right here. These are the terminals, and this is the ablation front. So as the ablation proceeds from the left to the right, it wears out this material, and as it wears it out, it changes the length, and as it changes the length, it changes the capacitance. So there's a direct relationship between the changing capacitance and the changing length. So that's basically how it works. We have been able to batch fabricate this sensor, which results in low cost manufacturing. After fabrication, it can now be diced into various discrete devices. In this case, here are some discrete recession sensors. And in this case here, this is an integrated recession and temperature sensors. This is an example of how a discrete recession sensor can be inserted into a thermal protection system, or an integrated version inserted into a thermal protection system. How does it work? So we took one of these test article and exposed it to a simulated entry condition, and looked at the voltage. In this case, we have converted the capacitance to voltage, and we looked at the voltage in real time as the recession continues. All right, so here's an example of how it behaves. So as it's receding, in real time, you are monitoring the voltage as this material recedes. So this kind of reflects how the sensor will behave in a real environment. So I would like to conclude by stating that we have successfully developed a silicon carbide piezo-resistive pressure sensor that's capable of operating of up to 600 degrees C and beyond, actually, for short durations. And as a result of this of developments, we have been able to control and to a large extent eliminate the offset drift that's very common in sensing devices. We have largely eliminated the thermomechanically induced failures. Of course, like I said before, the thermally stable ohmic contact that we have developed, it helped actually in reducing the problem of drift. By introducing the MEMS direct chip attach, allows for high density packaging and the elimination of wire bonding. So this work, as a result of this work, it's now possible to apply the silicon carbide pressure sensors for long duration engine ground test and potential short duration flights. I have also talked about our implementation of the first generation capacitive recession sensors, and whose application in real time will allow for monitoring of ablation, attrition, and wear. That's the end of my talk, and thank you very much.